Hello everyone, I'm Hussein Haydari and I'm going to be your instructor for these couple of lectures on polymers. We started our discussion in the last lecture about polymers. We introduced some concepts in terms of the definitions, what a polymer is made of, how these structural features and the chemical composition of a polymer can influence its mechanical and chemical properties. And we brought up a few different polymers that are frequently used in industry. And so you kind of got an idea of the breadth of things you can do with polymers in terms of applications, but this is just the tip of the iceberg. There's lots to discover, and hopefully in the next few lectures we will talk about different aspects of polymer chemistry. We talked a little bit about production of polymers and how we synthesize these large macromolecules, and we will talk more about that, as well as basically some main structural features that determine whether a polymer shows a particular behavior or not, and whether it's suitable for your application or not. So I'm going to pick up where we left in the last session. We talked briefly about how we synthesize these long chain molecules, and one such method, which we use quite frequently, is free radical polymerization. So in free radical polymerization, as we discussed, you have a free radical molecule that starts a cascade of reactions by breaking or opening that double bond in a monomer and forcing it to become a radical itself. So what it does is that it sticks to one end of that monomer and then breaks that bond. The other end, the carbon, is now going to have one extra electron, so it's ready to form a new bond, and so it acts as a radical itself. And this chain reaction continues, and more monomers are added to this main backbone chain, and the reaction continues until it's terminated. Now, this reaction could be terminated in many ways, but the main point is that you have no control over what the length of these molecules are. So you can have a distribution of chain lengths, all the way from very small molecules to larger ones. And in this production synthesis cycle, there is no way to control having 100% of X number of monomers in terms of length. You will always end up having a mixture. And what you can do is you can then filter these out and basically extract a subset based on their size or weight, etc., etc. An example of this radical that bond is benzoyl peroxide. Is an initiator. What it does is that you have a molecule, you break it somehow into two pieces, two radicals, and this is that initial step in the process where this is the molecule that starts this cascade. So how can you break that bond? There are multiple ways of doing that as well. One such method that we use, particularly in my research, is using light. So when you shine light, when you expose these molecules, amongst many other ways to transfer the energy, you can actually break this bond and, in other words, cleave this molecule into two radicals, which actually starts this reaction. So that's why it's a very interesting way to 3D print objects, is using light, and the way it works is just as I explained. So based on what I just said, you always end up, after the polymerization reaction, having a distribution of different polymer molecule lengths. So you can have all the way from few monomers to, so in this case, you have a distribution plot that shows you actually how many of your molecules fit in this particular molecular weight interval and how many fit in this interval. So looking at this, you can tell that the majority of the polymers that you got after the synthesis fall in this 20 to 25 times 10 to the 3 grams per mole of molecular weight. Similarly, you could have this for the number of monomers. Like, for instance, you would have, they're like, maybe the majority of these are 100 monomers in length. We will talk about that also in a bit. But the main takeaway point here was to remember that you can draw this distribution based on the number of molecules fitting in each of these intervals, which is the number fraction, or based on the weight fraction, which is how much of the weight of this entire sample that you've got is polymers with 20 to 25 times 10 to the 3 grams per mole molecular weight. How much of that weight is polymers with another molecular weight? So you can distribute these based on weight fraction, which is the percent weight consumed by that group, or the number fraction, which is much simpler, the number of molecules belonging to that particular group. So an example for that we had here, I'm going to get to that in a minute, but the way you then calculate this is that if you want to find the average, it can be either a number average or a weight average based on whether you use your weight fractions or your number fractions. And this was an interesting observation. I still haven't explained it. I'll leave that to you. That is why it's more frequent that we see the weight average larger than the number average. But before that, let's see what you use to calculate these two. If you want to calculate the number average molecular weight, you find the average based on these number fractions. So you sum up all the number fraction molecular weight products in that table or in that plot that you saw there, and that will give you the number average. If you want to calculate the weight average, you find the product of the weight fraction and the molecular weight belonging to that particular column, and then you sum up all these products to find the weight average molecular weight. Another way to do that is a lot easier, is if you had the overall weight of your polymer sample and you also knew how many molecules you had, then you can easily just divide those and that will give you the average molecular weight. So that is again a number average, but it depends on what data you've been given, whether you can use this formula or the other one. So we will have more examples on how to calculate this in class in the quiz, and also we'll solve a lot of these problems in class. But for now, I've actually brought an example that isn't from this concept is a lot broader. It's a concept in statistics that people use quite a lot, is either the number average or the weight average for any quantity. And in this example, it's the weight of students in the classroom. And what you've got here is in one column, we've got the number fractions. In the other one, we've got the weight fraction. And the way we calculated these was that, for instance, if I want the number fraction for this particular weight, I have to divide the number of students with that weight by the overall number of students. So you've got 0.2 or 20% of our class, in terms of a number percentage, has a weight of 220. Now, if I were to calculate the weight fraction, I would divide the weight consumed by this group, which in this case, we've got 2 students, each have 220, so that's 440. I divide that by the overall weight of the entire class. So I have to sum up all the students' weights, and it will give me 1860 pounds. And then I divide that 440, which is the overall mass or weight of this this class of students, which is like 220 pounds, by the total weight, and that gives me the 0.237, which is the weight fraction belonging to this class or category of weight. So once you've calculated these fractions, now you can calculate the average mass. And the way you do that is you multiply the fraction by the mass. So you've got the products of these two columns and you sum it up and you get the number average. Similarly, you find the product of the weight fraction and the weight respectively, and you sum up all of these products and you get the weight average mass. So it's a pretty simple process, but just make sure that you don't make excuse me, a mistake in calculating your fractions, because then that would influence your overall result. So there's another metric too, which is degree of polymerization. So degree of polymerization is the number of monomers in a chain, which is a lot simpler than molecular weight. This is just simply how many monomers connected together to form this chain. And in this case, for instance, our monomer has 2 carbons. So this is a polymer that consists of 6 monomer units. So you've got a degree of polymerization of 6. So it's interesting, you have, similar to molecular weight, you can find a number average degree of polymerization, and you can have a weight average degree of polymerization. So again, to use each of these, you have to find the number fraction or the weight fraction of each molecule. So for instance, if you had a distribution, this time instead of molecular weight for basically degree of polymerization, you would be able to use this formula and calculate each of these products and sum it up. So this is, again, pretty simple. It follows the same concept, it's the same formula, but rather than finding the average for molecular weight, here we're finding it for degree of polymerization. Now, degree of polymerization is really important because it tells us how far you've gone in terms of your reaction, okay? So if you have a degree of polymerization that's really small, that means that you either didn't give the reaction too much time, so all the molecules were terminated pretty soon, or maybe you didn't have enough energy in that reaction, the temperature was low, or it could have been you didn't have enough of the initiator. If you have a larger degree of polymerization, what that means, like if you have 100, 200, even 1,000 monomers in that chain, what that means is that you gave it enough time, or there was enough energy, the temperature was higher, there could be a lot of factors that influence that, but you ended up getting a rather long molecule. So now that we've defined number average and weight average degree of polymerization, we're going to talk a little bit about molecular shape. So this is a distinct part of this lecture series. We're going to look at how the conformation and configurations of these molecules differ, what we mean by conformation and configuration, and how these can influence the properties of your product. So you're probably familiar with already, molecules are made up of bonds. They could be single, double, or triple bonds, and we've come across that earlier as well as atoms that are connected by these bonds. And these molecules can be reoriented in space. So you can actually rotate them, but there are some things you cannot change without needing to change the chemical structure and basically break some bonds. So you can easily rotate this atom, as you can see here, about this cone here and about this other bond that you see, but you can't change this 109-degree angle. This is a fixed amount coming from the molecular and atomic equilibrium state and all the force fields that are holding these atoms together. So you cannot change this angle, you cannot change the length of this bond, but you can actually have this atom rotate about this point without needing to break a bond. So just based on this simple philosophy, we can actually understand how polymers, these long chains of molecules, can change their orientation and shape without changing their actual identity. So, for example, here we have a chain of monomers. You've got a polymer chain here, and you can imagine how each of these atoms can freely rotate there and therefore get into these equivalent. The molecule is still the same, they're just reorienting themselves in space. Now, it's really important to remember that it's not always as easy as they can just rotate however they want to. Depending on what you have in these side groups, and depending on the strength of this bond, it may force the next atoms in the chain to stay in a particular orientational configuration. So that's why you can do some stuff, but you can't do others. So, just to make it clear, some changes are not achieved by just simply rotating these. For instance, if you rotate this molecule that you see here, however much that you want to, you won't get to this molecule because this one here is a mirror of that molecule. So if you keep rotating this, you're never going to get to this shape here. You can try it yourself. So when you're given two different molecules, make sure that you don't, by mistake, assume that this is just a reoriented version of that. Because in a lot of cases, you mirror the molecule, and that's an entirely different transformation. Now, what I was talking about earlier was that even this simple rotation may sometimes be limited and constrained. Now, this is where you actually talk about configuration versus conformation. So there are, in some cases, situations where you cannot simply reorient your molecule. So if you have a double bond, for instance, if you have a double bond, that double bond limits the movement of this arm here. So similarly, if you have a large side group, that also imposes constraints on the next atom here because of its huge force field that it's producing around it. And these are basically atoms repel each other like magnets do. So if you've got this present here, the other atoms are going to be constrained to a degree more than they were if this was just a hydrogen. So you can imagine that some certain force fields like this double bond or that side group can actually put limitations on how much rotation you can get. Now, for instance, if you want to get this R group there, over there, you need to break that bond into a single bond, then reorient it, and then bring it back to a double bond. So what this means is that you have to break that double bond so that it's now weak enough for this rotation to happen, and then bring it back to the double bond state. You cannot just simply do that when it was a double bond. Similarly, here, you could actually change this configuration in your synthesis process. You can determine that, but you cannot change that afterwards if this was a double bond. In this case, actually for polystyrene, you have indeed a single bond. So it can rotate, but because you have this large side group, it limits the rotation of the monomers next to it. So these are two examples of what can limit your rotation. But other than that, there are lots of other cases too. That's why this is just an introductory module towards polymer engineering. If you really want to understand why a specific polymer behaves in a specific way, you really need to look into the structure and look at all these exceptional cases that may happen. So knowing that, we're going to talk about isomerism. And what isomers are is that they are molecules or compounds with the same formula, but different geometries or different structures. So, for instance, here you have octane. It has 8 carbon atoms and 18 hydrogens, okay? So it follows the same formula that we discussed before. And what it has here is that this is a linear chain. You can reconfigure that into a situation where you've got isoctane and instead it has some branches here. So you still have the same number of carbons and hydrogens, but here rather than having a linear chain, you have a chain that has these branches coming out of it perpendicularly. So these two both share the same chemical composition, the same formula, but they actually have two different structures, two different geometries. So these two are called isomers. And I just want to do a classification before we look further into these isomers. Isomers can be stereoisomers or geometrical isomers. And this is what I'm going to talk about in the next few slides, is how these two differ. And each of these have their own subcategories, which we will briefly. So first, let's talk about stereoisomers. Now, what are these? Basically, these are isomers where you have a long chain, and these side groups can actually be shifted around. So it's basically an angular reconfiguration. But again, as I told you, because these side groups can be relatively large, you can't just simply go from this state to that by rotating it. So it's kind of locked into this state that you see here. And what you see here is that you've got an isotactic, so we define tacticity as the stereo regularity of the chain, or in other words, how these sequences are repeated. So in this case, all of these side groups are on the same side. It's isotactic. In this case, they alternate. So you've got one on each side. And in this case, it's completely random. So it's the atactic isomer. So these isomers, we call them stereoisomers, basically have the same chain structure, but the side groups are rotated and shifted in and out. Now, this could be completely different. It could be that this is just one very specific type of isomer. What I showed you in the previous page, the previous slide, was that you completely broke this linear chain into a branch structure. Now, this and that are not stereoisomers. These are completely different molecules in terms of isomerism. They don't fall in a particular class. They're still isomers, but these classes are some specific types that happen rarely, and they don't cover the entire spectrum of isomers that you can have. So this is a very special case where you have only the side groups and their position are the distinctive feature of these isomers and what makes them different. So another class is isomerism of the kind cis and trans. Now, understand this better. Each polymer has a main chain. So it's the backbone of the polymer that runs through. And in this case, you've got a chain going there and a chain going here. Now, without that chain, you have other side groups. So for instance, here you have a hydrogen side group and a methyl side group. So here you have these two on opposing sides. Here you have them on the same side. As simple as that. The idea is that these two are again isomers, but one of them has these side groups on opposing sides. One of them has them both on one side. So again, this may not be a significant issue if these were able to rotate. But since the side group here is a large one, it limits the rotation. And apologies, this is actually supposed to be a single bond. It's not a double bond. There's been a mistake there. And it is not because of the double bond that the rotation is limited, it is because the side group is actually rather large, and so it's imposing a constraint on how much this can rotate. And it's interesting to know that just this very subtle change in the way the configuration of these polymers are can induce a significant change in their properties. So one turns out to be natural rubber, so it's a cis isoprene, and the other one is gutta percha, the trans isoprene. And you may not have heard of this, but this is what you have. This is natural rubber, which you've seen many times, extremely deformable and soft. This is gutta percha, a very rigid and stiff material. In the old days, they used to use this. It was derived from a tree derived chemical, and so it was manufactured with a tree derived chemical, so it was very biofriendly. But at the same time, it had some very interesting properties. They would use this for manufacturing golf balls. Extremely hard, extremely impact resistant, and at the same time rather rigid and hard. So you can see very distinct performance coming out of just the configuration being different. Another use case for this is now for root canals in dentistry, and you can look at those in the literature. So now we're going to talk about the molecular structures in terms of their chain configuration. So molecules can be configured in many ways. So specifically polymers, they could be linear, like what I showed you a few slides ago when I was showing the octane. If you remember, this is a linear chain. So all the carbons are on the same chain, and it forms a very long chain. Similarly, you can have branched chains like the other one that you have here. Instead of having them all on the single line, you can have branches splitting out, coming out on the side. Now, these are two of these classes. So you can have linear polymers, you can have branch polymers, but then these polymers can also have crosstalk with each other. So what that means is that they can bond together in order to form a cross-linked network. So you have these long chains of polymers that are then connected together to form a rather dense network or mesh, which is a cross-linked network. Now, if it's a lot more organized than that, it becomes a network when it's got a repeated unit. So they can just be randomly cross-linked as they meet each other, or they could be networked. Now, don't mistake this with non-covalent bonding, because these polymer strands could be connected together with some very loose chemical bonds called non-covalent bonds. These are actually covalent bonds, meaning that these are connected together with an actual chemical bond that keeps them together as an entire mesh altogether. And you can imagine that the strength of these polymers can increase by increasing the cross-linking density and the network basically formation. Another interesting topic is the length of these polymers, or the end-to-end distance. Now, if you remember from the conformations part, which I just had a few slides ago, these molecules here, these large polymers, can rotate in space in a lot of these cases. And so it can go from a long linear molecule, a molecule that bends and twists in space and has these very weirdly different tangled conformations. So based on how these molecules are entangled, you can have a very long spirally tangly web that starts from one point and the other. So it is not a trivial process to calculate the length of the polymer, as you can see here. There are some simple formulae to do that, but since it's a rather broad topic and it requires simulation in a lot of these cases, there's no need to go into depth there, but you can imagine that there are ways to compute that if you know the length of each bond and if you know the angles, you can actually then predict how long this can be, or at least get a distribution of lengths for the end-to-end distance. But I'm going to leave it at that here. So lastly, we're going to talk about copolymers. So copolymers are the case where you have two or more monomers polymerizing together. So what if instead of the same monomer, you have different types of monomers connecting together to form a polymer? So what do I mean? So what I mean here is that you can have two different types of monomers, A and B, that alternate within the same backbone. So here you've got a very nice pattern. You've got 1A followed by 1B and then again 1A, 1B. So you've got an alternating pattern. It could also be randomly engaged within the same chain. So you've got a number of molecule A followed by a number of molecule B and so on and so forth. And you could also have a block configuration where you have a number of A's together followed by a number of B's. And so there are lots of ways they can do this, but this one's a special one. This is a graft structure. And what it means is that you first probably form this backbone of A, and then you have these branched B chains connecting to the A. And this actually induces a lot of interesting properties because you've got a secondary copolymer that's actually been added to your main polymer configuration, probably in a sequential process. Once you've already synthesized this, now you're adding this, and it produces some rather interesting properties. Hopefully we can get to some of that in the future. So talking about polymers, their configuration and geometry, we've already discussed copolymers and the molecular structure and distance. The next topic is polymer crystallinity. And before we get there, I'm going to give you a break. This is another long lecture. So we will leave it at here and we will continue talking about polymer crystallinity in the next lecture. Talk to you soon. Bye.